Good day, dear students. Imagine you're calling out to your friend across a large hall, and yet, suddenly, no sound reaches them. What could go wrong? Today, we are diving straight into the reason why sound needs a material medium to travel. Sounds like a mystery? Let's unravel it. Sound waves are mechanical waves. That means they rely on the shaking or vibrating of particles in something like air, water, or even solids. These particles pass along energy by bumping into each other, much like how a row of dominoes falls. But here's the catch. If there's nothing to shake, nothing to vibrate, sound has no way to travel. Picture sound trying to cross empty space, a vacuum with no air or particles. Since no particles exist there, sound waves can't propagate. No medium means no particle vibrations, and without particle vibrations, there's no transmission of sound energy. Contrast this with electromagnetic waves, like light or radio waves, which happily travel even in a vacuum without needing any medium. Sound, being mechanical, is simple yet strict. Without a medium, no sound. So next time you hear silence in space movies, remember, it's not just dramatic, it's science. Array, simple and fascinating, right? Alright friends, now that we know sound cannot travel without a medium, let's explore exactly how sound moves through one. Sound travels by oscillating particles. Think of each particle as a little dancer, moving back and forth about a resting spot. These dancers don't travel with the wave themselves, instead, their vibrations pass energy from one to the next, creating the moving wave. This particle-to-particle interaction is essential and only happens when matter exists between the source and listener. Sound waves have some key properties: frequency, wavelength, and velocity. Frequency, denoted as F, is how many oscillations happen per second. Wavelength, lambda, is the distance between two consecutive peaks. And velocity, v, is how fast the wave moves through the medium. These relate in a neat formula you love: v equals f times lambda. That is, velocity equals frequency multiplied by wavelength. Keep this in mind: a vacuum simply doesn't support the oscillatory motion of particles because there are none. Without particles to oscillate, mechanical waves simply cannot move through a vacuum. Now, quick question: if the wavelength stays the same but frequency increases, what happens to the velocity? Yes, the velocity changes depending on the medium, so frequency and wavelength adjust to keep things balanced. Excellent beta. Friends, let's look at a classic experiment that beautifully proves sound needs a medium, the famous bell jar demonstration. Imagine a small ringing bell placed inside a glass jar filled with air. Now, as air is slowly sucked out by a vacuum pump, what happens? You hear the bell chime clearly at first, but as the air disappears, the sound fades away until it's completely silent, even though you can still see the bell vibrating. This shows the magic clearly: vibrations alone don't guarantee sound. The air, or more generally, the material medium, is crucial for carrying those vibrations as sound rays to your ears. Without air inside the jar, the sound energy has no way to travel, making the ringing bell silent in the vacuum. This experiment is a direct, practical proof that mechanical energy of sound requires a medium. So, next time you hear a bell chime, remember the unseen dancers, the particles that carry the sound to you. Shabash, friends, science is so amazing. Now that we understand sound needs a medium, let's peek into how we mathematically describe this sound wave motion in the particles. When sound moves, the displacement of particles at a position x and time t can be written as y of x comma t equals y sub m times sine of kx minus omega t dot. Here, y sub m is the amplitude, the maximum displacement of particles, like how far the dancer moves from their resting spot. K, called the wave number, is 2 pi divided by lambda, that is, 2 times pi over the wavelength. And omega, the angular frequency, equals to pi times f, 2 times pi multiplied by the frequency. A material medium plays a vital role here. Its particles provide restoring forces, like tiny springs, which pull the particles back as they oscillate. This restoring force allows energy to transfer successfully from one particle to another, carrying the sound wave forward. Let's solve a quick example to cement this idea of sound failing to travel in a vacuum. Suppose we have a bell inside an evacuated chamber, meaning the chamber has almost no air inside. We want to prove that sound transmission fails in this case. We start from what we know: sound needs a medium. In vacuum, number density n of particles is 0, no particles, no medium. So, transmitted sound energy T is 0, that means no sound reaches outside. Now, from Newton's second law, force equals mass times acceleration, F equals ma. If mass m is 0, no particles, then acceleration a is 0, no particle movement, no vibrations transported. You see the connection? The result is clear and observed experimentally: absolute silence, no sound beyond the bell's physical vibrations. This matches theory perfectly. Sound transmission depends entirely on the presence of material particles. Shabash beta! You just proved a fundamental law of physics. Let's wrap up what we've learned today. Recall the relationship V equals F times lambda. Sound's velocity equals frequency multiplied by wavelength. We also saw the displacement equation y of x, t equals y sub m times sine of kx minus omega t, describing particle oscillations. Mechanical waves like sound need matter, particles vibrating and passing energy along. No matter means no transmission. In vacuum, since there are no particles, mechanical energy can't travel and we hear nothing. Finally, speed of sound depends on the medium's density and elasticity. Without these properties found only in material media, speed is 0 in vacuum. So, next time you think of sound, imagine those busy particles dancing and passing on the beat. Excellent friends! Keep these foundations strong and let's hear the science loud and clear in future lessons. Shabash and keep learning!